So welcome to you as well from wherever around the world you may be. And I'm going to apologize in advance for what will be a rapid departure upon completing the session because unfortunately, due to travel plans outside my control, I literally have to catch a plane out to Warsaw like at literally at 10 o'clock when we end the session. So I'm going to pause at logical breaks, to take questions to see if there are any. But in the event that I'm not able to take a question because I need to run, let me make sure that you have my contact info. I guess that is one of our partners to thank for the event, DB Watch, and there's my info. Go ahead and just shoot me an email. I will respond. Definitely will respond, and certainly it might be a little delayed if I'm still traveling before I get a chance to get you a good response. But otherwise, about me, my name is Lenny Lobel. I run my own company back in New York City called Sleek Technologies. Welcome. And I'm also a Microsoft consultant with Ernst & Young, 11-year Microsoft Data Platform MVP. Lots of speaking and writing, old books down there, newer Pluralsight courses available over there. There is a Pluralsight course on this content and lots of other Cosmos DB content. So if you need more depth at perhaps a slower pace than I'll go this morning, definitely check out those courses. And welcome to everyone that's joining. And it is now 9 o'clock sharp, so I'm just going to jump right in. There is this deck, and there's a minimal amount of code for the demos that I'm showing, but all my code is part of one large workshop solution that you can download from this link. I just checked before the session, make sure that it's working. Welcome. And it is available for you to visit and download a zip file that will have the full workshop session code as well as this deck. And if you need me to put that back up there, I'll give you a chance to take a photo. Excellent. So what are our objectives today, this morning? Well, certainly for those of you less familiar with Cosmos DB, we are going to get familiar with some of the core concepts. Not all of them, not in this hour, and especially since that's not our focus, but just the ones that you'll need to, the real critical core concepts that you'll need to follow along with the rest of the session. And we will look at the best practices for data modeling in Cosmos DB. And we'll do that by applying the concepts to something that we can all relate to. I mean, how many of us have worked with SQL Server? Right? So we all know and love AdventureWorks, perhaps Northwind and Pubs. I don't see anyone old enough to remember those. Maybe some, maybe not. But they all have the same concept, right? They're the relational data models in a traditional SQL relational world. And how is that different from a more modern NoSQL non-relational database, such as Cosmos DB, when we're trying to implement something that is relational? So what is Azure Cosmos DB? That is a loaded question with answers that I could ramble on for the entire rest of the session, but for the purposes of just this session, right, like I said, if I started going down the list, and there's so much, its key points are that it's globally distributed, it's horizontally partitioned, schema-free, multi-model, but I could go on and on and on. For this session, the only two concepts you need to lock down are horizontally scalable and non-relational. You lock down those concepts, you get the concept of partitioning in place, and you will be able to follow all of the all of the aspects of this session. So let's break those two terms down. Horizontally scalable means what? Well, we have a logical container. It is a logical resource that we interact with as a single resource. We store and retrieve JSON documents into and out of that container. But of course, behind that container, that we don't manage this, but there is a cluster, right? There are a set of nodes, if you will. There are a bunch of servers there, and the more you need, the more you get, and so on and so forth. And there is no real upper limit to the number of, let's call these physical partitions, if you will, because they were going to physically partition your data, but they're like servers, essentially. Each one has a CPU, and each one has storage. So the more you add, the more CPU and the more storage you get, at the risk of oversimplifying what's actually happening. But in theory, if you partition your data properly, you will never run out of throughput or storage, ever. Of course, you have to, right? You'll have unlimited storage and unlimited throughput, but you'll have to make sure your data is partitioned properly in order to achieve that. So what was the second topic that I mentioned? The second definition, rather, which is that it is non-relational. So in the relational world of SQL Server and Oracle and MySQL and Postgres, et cetera, we live in a world of normalization. What do we love to do with rows? We love to join them. We thrive on optimizing the best data model that is highly normalized, and we rely on the database to join data that's related together on primary and foreign keys, etc. And however, in the non-relational world of Cosmos DB, we are storing data not in rows, but in JSON documents. And there's certainly nothing you can store in a row that you can't store in a JSON document. Right? You can just put everything that you used to put inside of a row and stick it inside of a JSON document, and in theory, at least, have pointers from one JSON document to its related child or parent, if you will. And there's nothing stopping you from doing this other than you'll be out of a job very quickly. It'll be a very poor design. This will break down. Why will it break down? That ties back to our first point again about this being a horizontally scalable system where each of these so-called related documents, they could land on physically different servers. And not that it's technically impossible, but by design, Cosmos DB will not enforce any kind of referential integrity between one document or another in order to maintain its very high performance levels. And nor will it join related documents together. So there's no joins, there's no constraints, and it makes you wonder, well, then is it at all suitable for relational workloads where we rely on joins and constraints? And the answer is, of course, it is, because the session would come to an end at this point if the answer was no. I mean, if it was not suitable for relational workloads, I would have nothing more to talk about other than to discourage you from using Cosmos DB. But when you need that massive scale, you can implement a relational design, but you need to think about things very, very differently than you do in the normalized world of relational databases. It's kind of like a different approach. It's an approach where many of the best practices and your intuitions, for those of us that have been doing this for years or decades even perhaps, it really goes against the grain of many of those best practices. And you'll see exactly, well, I've already started kind of giving you the reasons why. Like, you can't rely on joins and constraints when you don't have them. And if you do, you won't have a very good design. So to break this down, what I did was I took AdventureWorks and I reduced it to a database with 9 tables. And I have the scripts for you to run if you want to do the same thing, if you want to practice this exercise yourself, to use this 9-table relational database as a starting point, which we will refactor into Cosmos DB for an optimal design. So what do we have in these 9 tables? There's only 9 tables, but it covers like the vast majority of the design patterns that we use day to day in our SQL life, which are one-to-many relationships, like you will have between customers and addresses, one-to-ones perhaps between customers and passwords. You'll have a product table with a parent categories table, right? So each product belongs to a category. You'll have a one-to-many there. You'll have that many-to-many relationships implemented through junction tables, like product tags, where a product can be associated with more than one tag, and a tag can be associated with more than one product. So you have that, that kind of many-to-many junction table there in the middle. We've got another one-to-many of sales orders, the sales order details. And of course, it is a 3-level hierarchy because one customer has multiple orders, one order has multiple details. So we've got, multi-level, many-to-many, one-to-many, basically your typical relational database reduced down for our exercise today. So your first intuition might be, I have 9 tables, should I create 9 containers? hopefully I've already given you the answer to that question and told you the answer to that would be no. Again, there would be nothing stopping you from doing this, but if you're wondering if it's a good idea or not, certainly it is not a good idea. Again, you're going to have to retrieve all the related documents individually and separately. You're not going to get any joins performed for you by the database platform, nor will you have any referential integrity. So let's start refactoring this. Let me pause now for questions. I mean, there shouldn't be that many because I've just kind of like laid the stage and I haven't really kind of dumped the concepts on you, but any thoughts or concerns, just shout them out. If none, silence is compliance. I will just move on and look, and let's just break it down as customers and our customer related data. How can we refactor this set of tables, this subset, if you will? And step one is going to be to translate your columns that are defined in your tables to JSON properties, JSON document properties. And you'll do that. What I've done here is I've just camel cased them all. And that wasn't strictly necessary. But that's the generally accepted and adopted convention in the world of JSON. And the one thing that I didn't have a choice on was the ID property. There's the concept of a primary key in Cosmos DB is that you have an ID property and it has to be called ID. Excuse me. And so therefore, I've named the property ID. But other than that, I've done nothing other than a one-to-one translation where I still have these kind of like, and I'll use air quotes because they're not really foreign keys. Let's call them references, where one document references another through this customer ID property here, if you will. But because this is JSON data, we can combine all this data into a single document. Can and should. And when should you and when shouldn't you, we'll talk about. But in this case, we should. And we'll talk about the reasons why in a moment. But you see immediately, once you nest related child data beneath its parent, you have inherent referential integrity. A child can't live without its parent. So, the idea that there's no referential integrity goes away. And it's also pre-joined, right? Once you are pre-joining your data, you're kind of like joining the parent customer with all of its child addresses, pre-joining them, if you will, in the document, then you eliminate the problems of having no joins if you pre-join. So this is embedding an array. I only have space to show one, but you see it's an array. I could have multiple addresses, not any number, but a reasonable number. And certainly the password couldn't be a nested object because it's one-to-one. So embed versus reference. When to use which? Well, this is embedded. This is referenced data. When to use which? Well, often when it's a one-to-one relationship, often when it's a one-to-few relationship, meaning there's child data, but it's not like this unbounded. Like, I wouldn't be able to consider storing customer orders as children of customers in a single customer document. That will grow too large. Right? Ideally, we don't want any upper limit on the number of orders a customer can place. So we're not going to embed that into a document, certainly. But we can certainly impose a reasonable number, an upper limit of number of addresses that a customer can define. Let's say we're building a customer-facing website where the customer logs in and they manage all their profile information. Well, in that case, all of that data is typically going to be queried and updated together. You're going to pull the customer with their related information, profile information, if you will, addresses, addresses, passwords, etc. Present them on a profile page, allow the user to update that information. So it's going to be queried and updated together, all the reasons why you would want to embed. And a reference is when it certainly wouldn't fit, like a one-to-many or an unbounded relationship. A many-to-many relationship, as you'll see in a moment, where actually it's a combination of embedding and referencing. We'll cover that in a moment. Or even if it is one-to-few, but they are rarely retrieved or updated together, and it probably still makes better sense to keep them separate because they don't reference each other that often, and they're certainly not queried or updated independently. So based on that criteria, we're choosing to embed, and we're going to store what used to be contained in 3 tables in the relational model inside of a single document, inside of not a table but a container, which we'll call very originally the customer container. It's going to store these customer documents with nested addresses, embedded addresses, and passwords. And now we have to ask our question, our very all-important question, how do we partition the customer container? Well, for that, my friends, we are going to pivot to the topic of partitioning, cover that, and we will then revisit our little exercise here and apply these concepts. So what is partitioning? We started explaining how you've got a cluster of servers, if you will, or physical partitions behind each container. Let's drill into 3 of them. And again, JSON documents are going to land somewhat arbitrarily on any one of these physical partitions. And now we ask the question, how does Cosmos DB know which partition to store or retrieve a particular document? If there's going to be an unlimited number of partitions, there needs to be some logic to this. And the answer to that has to do with logical partitions. So the big black boxes, those physical partitions, those are managed entirely by Cosmos DB. We have no control over those. But by defining what is called a partition key, we define these logical partitions. Those blue bordered sets of documents are all kind of grouped together by the partition key that we choose for our container. And if I pivot now to an example that's like social media based, where we're dealing with users and posts and comments and likes and that sort of thing, I might choose the username property to be the partition key, which would mean, and if we sort of forget about those physical partitions, which is for the most part, we're supposed to be able to not think about those physical partitions, right? Because they're managed by Cosmos DB, and focus just on the logical partitions. In this scenario, it would mean that all of the user's documents, Tim's documents, are all grouped together separately from Andrew's and so on. But that these individual documents themselves are of different types. Like the first document in each logical partition could be the one profile document that you have for each user. But then like this next set of documents here might be Tim's posts. And then the next set of documents might be Tim's comments on other users' posts, which have a different schema, different structure than posts. Comments and posts are different, and then maybe several documents are structured as likes, like documents, when Tim has liked other users' documents. So they all have different schemas, so it's very different than the way you think of how you define a schema of a table in a relational database, and you store everything in its place. But the one thing that they all have in common is that one username property with the same value, Tim in this case, that kind of groups them all together, logically as well as physically, because these logical partitions will never span physical partitions. And if Cosmos DB knows which logical partition to go to, that's the ideal query scenario for performance, so that it shouldn't have to scale it, or fan its query out across the cluster. So now important constraints to bear into consideration might be the document size, 2 megabytes. That's your maximum upper limit. Can certainly comfortably accommodate a set of addresses for a customer, but not all of their orders. It can certainly accommodate an order with all of its details, though, as well. And the maximum logical partition size is 20 gigabytes. So that's a comfortable number. Ideally, your logical partitions will never approach anywhere near that size. You want your logical partitions to be relatively small, discrete units with our groups of documents that are grouped together. Let me do a quick time check. Okay, so the beauty of Cosmos DB are partition splits that occur automatically and transparently in the background. Thank you so much. So what happens is that when a partition becomes too busy, and by busy I mean either full in terms of storage or overloaded in terms of throughput, like in terms of demand, it's just too much for one physical partition, especially if you have provisioned and therefore are paying for a higher degree of throughput than can be achieved by the demand coming into one physical partition. Cosmos DB will spin up a new physical partition and move roughly half of the logical partitions over from the partition being split, and kind of rebalance the whole container and allow things to continue on. So you want to avoid hot partitions. Something that looks like this just visually looks wrong. it just doesn't look like from a storage perspective we're really able to utilize the scale out capacity, because most of our documents are sharing the same partition key, and they're therefore kind of like locked into one physical partition. And that logical partition has an upper 20 gigabyte limit. So this doesn't look like a good partitioning scheme. You have a hot partition on storage in this scenario. And this, while it may look better, and is better, certainly from a storage perspective, again, depending on your throughput or data access patterns and the types of queries that are most common in your scenario, date is often a poor choice. It's often one of like the wrong choices that people make. So it sounds like a good partition key from a storage, because it is from a storage perspective. But if the vast majority of queries are hitting current data, particularly today's data, then all the throughput. When you provision throughput on a container, you provision and pay for the number of request units per second, RUs per second, that you are that are provisioned, that are guaranteed to be available. But those RUs are distributed evenly across all the physical partitions in the container. So in this example where there's 3 physical partitions, if I had provisioned 30,000 request units per second to be available for the container, and I'm paying for that, that's 10,000 per. And all the queries are hitting the one partitions. I'm essentially paying for 30,000, I'm getting 10,000 for most of my queries, because there are very few queries that are hitting the older data. So that's a hot partition on storage. And that's why, again, coming back to, that's a hot partition on throughput. So we saw hot partitions both on storage and throughput. And that's why, again, the username is probably the best choice. It's going to give us, like, the more users we have, the more this thing will just scale. It'll add logical partitions. It'll fan out. It'll partition split as we get more users. All of the users' documents are grouped together. So cross-partition queries are what they sound like. So if the partition key is known for a given query, this is a single partition query, the most efficient type of query in Cosmos DB. If most of your queries are single partition queries, you have a good design. Notice I said most, not all. It'll never be all. Don't strive for all. You will over-engineer. You can and will over-engineer. But strive for the 80% or better case, especially in high-volume scenarios, especially in IoT scenarios, where there's high volumes of data being emitted by devices, or even, like, let's say, large-scale e-commerce scenarios where you've got hundreds of thousands, if not millions, of concurrent shoppers around the world. Think in terms of those scenarios. If the partition key is known, then it becomes a single partition query. Like if the username is the partition key and I'm looking for Mark's documents, Cosmos DB knows which logical partition to go to, and it doesn't need to be all of Mark's documents. It could be filtered on date. It could be filtered on type, right? It'll still be a single partition query, and therefore, if it knows which logical partition to go to, it knows which physical partition to hit, and not this fan the query out. Like, this is an equally innocent looking query to get all the documents, because we want all the users whose favorite color is red. Obviously, this is a cross-partition query. And if this is not the majority query, but kind of like the minority query, then it's perfectly fine. But it does mean, because the partition key is not known, that the query needs to fan out. And therefore, every physical partition needs to be hit. Is it inherently evil? No. The cost for hitting a physical partition that has no data is 1 RU. No one is going to hurt or notice an RU here or an RU there. But if your vast majority of queries are hammering away in a high volume, high throughput scenario at cross partition queries, then it becomes a problem. Right? Okay, let's come back to our scenario. So what are we going to partition? The answer to that question always is with another question. What are my most common queries? And in our customer-facing website scenario, at least, a customer is going to want to get all of their information, right, for that profile page. They're going to want their name, address, and phone number, as well as all their addresses, perhaps their password as well, perhaps to change any of that information as well. So basically, it means I'm going to want to query this typically in most cases by the customer ID, which is, of course, the ID property itself. which means that I would actually want to choose the ID property itself as the partition key, which creates a strange scenario where your logical partitions can only ever have one document in it. And which may sound odd, and certainly from a querying perspective, as I was just describing, where you want to group related documents together for performance reasons, this doesn't satisfy that. But for this vast majority use case, we want a key value store. That's just basically what we need. Given a customer ID, I want you to get it's just a key value. When you want key value, you choose the ID property as the partition key. And this gives you kind of a key value store. And it's also worth mentioning at this point that a document is unique within a container in Cosmos DB based on not just its ID property, but a composite, a combination of that ID property and whatever property you have chosen as the partition key, like the username in the previous example. Like the ID property is not enough to make the document unique in the container because it's qualified with the partition key, right? But if you choose the ID property itself as the partition key, then it's unique by that ID. It's globally unique, that's actually what we're going to do. We're going to partition on the ID property so that and let me just run a quick demo here because you're probably hungry for demos. I've got 4 versions of this web store database here, web store v1 through v4. v1 we've already discounted. It's got these 9 tables in it. It's not a good design. If I open up any one of these documents in the customer table, on the customer container, you're going to see a JSON document that is the equivalent of what was a row in that table in the relational model, like no embedded information. If I want the addresses, I have to go to the customer address table, and it's only one address per, and there's the related customer ID, but again, there's no joins, so this is a bad design. So we're going to actually, we've moved on to already to Web Store v2, which has fewer containers, as you can see, because the customer container has documents like we saw on the slide. Right? There's a customer with its embedded addresses in an array and its embedded password. Let me run a quick demo here, D1 for demo 1. I'm going to query for a customer knowing its ID. I know its ID. It's a GUID in this case. If there's time, we can talk about what the better choices, but we've got a GUID here. If you know the customer ID, then you run a select statement. Let's see what comes back. Yeah, there's the ID. There's Amanda Cook. And Amanda's addresses in an array, 2 addresses in this case, and a password, and some properties on the bottom that we don't have to worry about. They're just the underscore prefix properties there are system properties from Cosmos DB. We're not going to worry about them now, but it did retrieve one document at a cost of 2.83 request units, which is about the cheapest cost for a query. Like if it's a single partition query, it'll cost just about under 3 RUs, and the RUs start to shoot up once it fans out and becomes a cross-partition query. But now look at this next example. I want to retrieve the same customer by its ID, but this is a key value store, right? If you know the 2 things that make a document unique, which is the ID value and the value of the partition key, and if you choose the ID as the partition key, then it's really just the one value repeated twice. The ID of the desired property and the partition key, which is the same value if you choose the ID as the partition key. I am doing a read item operation here with the .NET SDK in C# and retrieving the same document at a cost of 1 RU. And it never gets cheaper than that. That is the cheapest operation in Cosmos DB, 1 request unit. Okay, so the point there, no pun intended, is that you should always do a point read over a SQL query if you can, if you just need to retrieve an individual document. So I'm going to try pause here, see if there's any questions to this point. We still have more concepts to lock down, so if you're wondering about certain other things, we're probably going to cover it. And we have product categories. This is going to be really simple because this is truly key value even in the relational database, right? We have a product category ID and we have the name. That's it. So it's really simple. It's the same process of converting that into JSON, making the ID name, the primary key property name to simply be ID, store it in a container, ask the same question, how do I need to partition this, answer it in the same way by asking what my most common queries are. Well, the customer has logged in, and now they want to browse, and they probably want, they want to first look at all the categories, and then they'll pick a category to drill down into products that are in that category. That's the most common case. So it's really a select with no where clause. Like if you were in the relational world and you stored all the categories in a table because you needed to populate a dropdown or a sidebar, a navigation sidebar or something like that, you would just store it. You would select from that table with no where clause. So that's kind of what we want to do. We want to basically, a logical partition can be up to 20 gigabytes in size. So any kind of like metadata that is not classified as big data that needs to be partitioned because of its volume, like small lookup lists, like product categories, you want all of them in one logical partition so that you can get all of them efficiently. The trick here, since we do need a where clause, without a where clause, it's a cross-partition query. We're just going to add where type equal category and set the type property as a category in every document that is a product category, and thereby bind them together inside one logical partition. Let's see a demo of that. So D2, demo 2, demo for querying for product categories. Here I'm doing a select from the container where the type equal category, and all of the documents have a type of category. So I'm getting all of my categories, which is really just the ID that I need and the display name. The type is category in every document, as I was just explaining, and all of these underscore prefix properties we really don't need as well. So we can make this a little bit leaner. Notice it was 3.85 RUs. If I, instead of saying select star, I specify just the ID and the name properties that I need to pull back from my drop-down list, if you will. And it's 3.87 RUs for the same 37 documents, and it pulled back just the ID and the name. The reason I call it the RUs is that it's interesting that it was 3.85. It would cost ever so 0.02 RUs. Like, it's negligible. But it's still interesting to know that I pulled back less data and it costs 0.02 RUs more. Probably to process that where clause, which I didn't have a where clause before, and now I do, so that costs. But it's infinite. It's not measurable, right? So those are product categories. Product tags are the same. They're just key values, so it's the same process. Convert it to JSON, stick it in a container. It's the same thing. We're going to want to maybe let the user, see all the tags and then get all the categories that are tagged with a particular tag of interest. Same concept. We want to select with no where clause. We'll just put all a type property in all the tag documents and set their value to tag in each one. Where it gets much more interesting now is that many to many, right? So for product category to product is one to many, but for tags we have many to many. How are we going to implement that? Well, actually, I'm sorry, I just got ahead of myself there. First products, then we'll get to the many to many. The products themselves, oh no, we're at the many to many. I'm not ahead of myself. I'm exactly where I want to be. I think I'm exactly where I want to be, which is right here. For product tags, because it's many to many, you do this with the combination of embedding and referencing. You embed, on one side of the relationship, you embed an array of references to the other side. So I am embedding tag IDs inside of each product document. I could be embedding product IDs inside of each tag document, and which one would be better would depend again on the usage pattern. But here I'm just storing the IDs there, and that's why I have the many to many. I'm storing the products inside of a product container. I'm asking myself how I need to partition it. I'm answering it by saying, what's my most common query? Well, there's a drill down here, right? The user already selected a category. The most common query for products is find me all the products in a particular category. So I want to query on category ID. That means we want to partition on category ID. I mean, there's a lot of oversimplification here because there could be more than one very common querying pattern. You can, you can have microservices replicating this data into other containers, replicating it except for partitioning it differently to satisfy other read-heavy scenarios. I am keeping things very simple for the exercise here of our little website where the user has picked a category and the most common query is to get all the products in that category. So I want to have all the products in category A in a separate, in their own logical partition so I can get them all efficiently. But now we have a new problem, right? We only are holding on to these IDs because we're doing referencing. We're not embedding, we're referencing. And when you're referencing, you don't get the benefit of joins like you do in the relational world. So the problem is that we don't have a category name or tag names. It's going to require additional queries. Like just to get all the products in a category, this will be efficient because I'm getting all the documents inside one logical partition. It'll be very efficient. But I won't have the category name because all I have is I was given an ID and I want to display the name. Well, that's a second query now on my product category metadata container on the category ID. And much, much worse, of course, is for each document returned by the first query, for each, I need to run this third query with that in predicate there to get all of the names of all the tags and all in the tags array of all the product documents. So where are my joins? But they don't have, pound your hands all you want. They don't exist. And the answer is denormalization. We duplicate data. We do things we would never do in the relational world, like we duplicate master data. In the interest of time, I'm going to just kind of speed up this, summarize this slide to basically say normalize versus denormalize. And in the case of denormalize, we are duplicating data. So in addition to the category name, in addition to the category ID, I'm going to stash a copy of the category name. And the tags array, instead of being a simple array of IDs, it is now an object array where each, tag has not only the ID, but a copy of the name. Now, in the master data, there might be more information about tags and categories, but in our most common scenario, we needed at least that information in most cases to be available without requiring the extra queries. So we want to duplicate that information. So at the point of insert, it's kind of a no-brainer. When we create a new document and we presumably know the category name, or at least we can obtain it somehow and store it in the document, but then the question becomes, what happens when the master data changes? In the relational world, if you change a category name, and then you do a fresh join, you see it duplicated instantly across everything that it joins with. How do we achieve the same thing? We do that with an Azure function, aka a change feed processor application, which could also be implemented as a microservice. In order to propagate the changes from whenever somebody changes a product category name or a product tag name. I'm going to show you how that works. So the change feed is this persistent log of changes. As documents are added or updated to the container, it gets emitted through the change feed. And the change feed itself is persisted. It can always be rewound and played back from the beginning. And the easiest way to implement this is with an Azure function trigger, which I'm going to show you how that works. But basically, I'm going to have two Azure functions that are triggered by changes on the change feed to either of these two containers. And that Azure function will wake up. Here's the code for that Azure function. That's the function name. I'm watching that particular container, the product category container, on a connection string that's configured outside this code here, using the least container, which is a container that is not part of our data model, but is required by the change feed to manage state, so that I can be stateless and I don't have to worry about state or scale. This function will automatically parallelize across multiple threads if necessary, and using the least container, we'll be able to have checkpoints to keep track of the last time changes were obtained, and if the service goes down and comes back up, it knows where to pick up, and all that happens automatically for you. And in terms of parameters that you get back, it's just the read-only list of documents, and that's all you need, and a logger to write output to, and you can just loop through each document, get the ID and the name of the changed data, and call another method that will loop through. I'm not going to detail this code, but I'm running a query to get all of the products in that category and changing and looping through each one, and there calling replace item to update that value. Let's see it in action. So I'm going to flip on over to the Azure portal, where I'm actually going to restart the Functions app. This is an Azure Functions app. And if I click on functions, you can see I've got 3 of them. So for this container, I've got categories and tags in 2 separate containers. So I've got 2 separate functions. In the next version of this data model, we can combine those. So that's the third function is for the next demo. So let's just look at sync product category name and monitor that. And come on back to the demos and run demo number 3, denormalization using the change feed, where I'm going to select 5, see there's a top 5 documents based on category. So, the first 5 documents in this category where I know that the category name is clothing shorts. And you can see that each document has a copy of that name. So that when I have this document, I'm ready to display it. I don't have to run another query. But what happens if that name changes? In the master data, these 5 documents, in fact, all the documents that have this product category ID have to be updated. And it will be using that code, if you that code that we just saw on the previous slide. So I'm going to read the category document so that I can change it. And I'm doing a point read, so I need the ID. I know the ID of the desired category, which is clothing shorts, which I want to change now to clothing fun shorts. And you need to know the partition key value, but that's easy because they're all category, right? We're partitioned on type. Every category document has the value type, so that's not really anything that you need to know beyond that. It's always hard-coded as category. Change the name to clothing fun shorts and then replace the document back into the container, update the document back into the container. So it retrieved it and it replaced it, and hopefully we'll see this wake up. There we go, it woke up. Change detected in one product category document. Oh, there we go, it just updated. Should say at the bottom there, I think it's 7 documents, seven product documents. So when we look at those top 5 again, look, each one of them have been updated, the clothing fun shorts. And that's how you go about that. I'm kind of just racing here, but we are racing to the end because we only have these 2 tables left, sales and sales order, but there's still some more goodness to come. Same process. By now it should be like routine. First process is you convert to JSON property names. Then you decide embed versus reference. We are certainly going to embed order details inside of each order and not have 2 separate documents, and certainly not 2 separate containers. With an array of details, what's our most common query? A customer is going to want to get their sales orders, right? Obviously, get all sales order for a customer. And there might be another query that's, let's say, less common, and therefore okay if it's cross-partition, but this is maybe for like a back office executive on their dashboard. They want to see always on their dashboard their top customers, right? So they want to see get best customers order descending by, let's say, order count. So let's go with the first one. This is the common one. This is the customer-facing website. Customer wants to get all of their orders. We want to partition on the customer ID, right? Every customer has a logical partition with their orders, and each of those order documents has sales order details embedded in it. So we want to partition on the customer ID, but now let's slam on the brakes for a second because I know I'm racing here. But this is not the first time we're partitioning on the customer ID. Our very first table, the customer table, remember we did it as a key value? We partitioned on the ID property. That value is the same value. It's the customer ID value. There it's in the ID property. Here it's in the customer ID property, but it's the same value. And therefore, we should consider, because there it is, right? There it is in the customer table from the customer container from the beginning of the presentation. Should we combine different types in the container? Cosmos DB is schema-free. You don't create multiple containers because you have documents of different types. In fact, it was wrong for us to store product categories in a separate container than product tags. I mean, these are small, tiny little lookup lists that can live in one metadata container, and they should. But certainly, when you have documents that share the same partitioning needs, which is the case here, and as well the same throughput needs, because you provision throughput at the container level usually, you can and should put them into one container. So I've got one container called customer, but there's actually 2 different types of documents in that one container. We have a little problem that we need to solve here, which is that the value in that ID property is different. Like it's the customer ID for a customer document, and it's the sales order ID for a sales order document, and it's it's this value here. That's the customer ID. What we'll do in our customer document is duplicate that value into a property called customer ID so that the ID and the customer ID values in a customer document will be the same. But because I now have a common property in two different types of documents called customer ID, I can partition the container on that property. And this, by the way, is why, in case you were wondering, and maybe you were going to ask, but I'll answer it now, why am I using GUIDs for the ID? GUIDs are not really nice. They're not very friendly, right? We don't like them that much. Certainly not if you have to memorize them and type them and reference them. But they didn't have to be GUIDs. They have to be strings actually in Cosmos DB. So even if it's an integer, you have to put it in quotes. But I could have just put a C in front of customer and an SO in front of sales order and kept the integer ID. But I couldn't have just kept the integer ID. Because in the relational world, I have sales orders in one table and customers in another table, and I can have the ID 1 repeat. That's fine. But if I'm co-locating them in one container, it's just that's why I chose that's why I converted them to GUIDs. It's also always a good idea to have a type property. With a type property, you can distinguish unambiguously. Instead of relying on some brittle logic that says, well, only sales orders have email addresses. I'm sorry, only customers have email addresses and sales orders don't. So if there's an email address, then it's a customer, and otherwise it's not. We don't want to do that, right? One day there's going to be an email address showing up on that type of document, and that logic is going to blow up in your face. So in order to help bring order to the chaos that can ensue when you are dealing with a schema-free database that doesn't care about schema, you have to care a little bit more about it and maybe be explicit about the types of documents you have, and maybe even add a version property that increments whenever you consciously change the schema of one of these things, because there's no friction as far as the database is concerned when the schema changes. It just accepts it. So now I've got two different types of documents in one logical partition. I've got one customer document and all of their sales orders. And now I can get all the sales orders for a customer with this query. Let's see a demo. Demo 4, querying for sales orders. I know the customer's ID and the type is sales order. What am I getting in one query? Two documents, which is one document per sales order, but each of those documents has embedded within them the details at a cost of 2.96 RUs. And look at this next query. I take out the type check from the where clause, and I get all the documents for a given customer. I'm ordering by type. It's a hack. The C in customer will make that customer document be the first document in the results set that gets returned, followed by all of their sales orders. And look what I've got. In one query that still costs less than 3 RUs, I got back a customer. This is based on most common usage patterns, right? Only. I got back a customer, their sales orders. I went back too far. Yeah. The customer, all their embedded addresses, pre-joined, if you will, the password pre-joined, all of their sales orders, and all of their embedded details. If you think about it, in a sense, I have gotten my joins back that I lost, because by keeping them all in the same logical partition, they are essentially joined effectively. Retrieving them together in one logical partition is like having them joined together for you, even though they're being referenced as separate documents. And certainly when they're embedded, they're pre-joined. What about our last query? That back office exec that's sitting back wants to see their top 10 customers. Well, we would normally, in the relational world, not even bat an eye at that. That would be a piece of cake, because it would be a simple aggregate query, a select count query with a group by. But that, again, we don't have the benefit of those joins to aggregate on the fly like that here. So it's just, the answer again is just a little bit of denormalization. Inside each of sales order, I'm going to have a property called sales order count with the number of orders. And every time that an order is placed, I'm just simply going to increment that number. It is basically reflecting the number of related sales orders that exist. So what that means is that when there's a new sales order for customer A, and I add that sales order, I also want to update that customer and increment that value. And if you're thinking change feed, that's good because we were just talking about it and it could be used, but we want something a little better perhaps, something that happens actually not in near real time, but in actual real time and with transactional integrity. We want to make sure that if the new sales order, if we increment the value in the customer, but we fail to add the new sales order or vice versa, that they both roll back. The answer to that is to use a JavaScript-based stored procedure, which I'm not going to walk through here, but it is effectively reads as read the customer document, increment the sales order count, update the customer document, but it doesn't get committed until the entire function succeeds. So then it can go ahead and try to create the sales order, and only if that succeeds will both be committed. So every time I want to create a sales order, instead of adding it directly to the container, I will pass it as a parameter to the stored procedure that is accepting the sales order document as a parameter. Let's see a demo of that, and I think we'll be done, or close to done. Demo 5, querying for top customers. So give me my top 5 customers, order by sales order count. So this is my last version of the I can show it to you here in the portal of the database. This is V4. V3 was using the change feed, and V4 is using the store procedure. Look, I only have 3 containers. It looks like 4, but that least container belongs to the change feed. It's for managing state, and if there's time, there might be, we can peek in there and see that it's just a time stamp. So it keeps track of when it last fed you changes. And if I open up the customer, you can see, well, I mean, actually, it's not, okay. Yeah, all right. Here's a customer document. You'll see there's a sales order count property. Right now, there's only 1 order for that customer. So if I queried for orders, I should only get 1, right? But I have that number pre-aggregated and therefore available for these queries. So going back to the demo, I'm going to select my top 5 customer. I've got Mason Roberts and Dalton Perez tied as top customer at 28 orders each, and then goes down 27, Daniel, and so on. So my top customers are bubbled up at the top. And what I'm going to do now is I'm going to create a new sales order document. See, I'm giving it a GUID ID. I'm setting its type to sales order. I'm referencing the customer that it belongs to, okay? And it has 2 orders in it. It has 2 details in it. And I'm calling execute stored procedure SP create sales order. That's the stored procedure we just saw. If I go back to the portal and I look at stored procedures for the version 4 of this database, there is SP create sales order. That is the same stored procedure that I just showed you in the slide. Bump up the font a little bit, maybe. That's really unfortunately tough to read, but there, that's the store procedure. Retrieve the customer document, increment and replace the sales order count in the customer document, then create the sales order document, and doing error checking along the way. And it keeps getting nested because you're dealing with callbacks instead of async and await, like you would with C#. This can be done in this is really old code from the beginning of time, practically, with Cosmos DB. You can do the same thing in C# if you want. Transactional batch, it's called. Let's go ahead and run it. Call the store procedure. It executed the store procedure. Run the same top 5. And there you have it. Dalton Perez is now surpassed Mason Roberts. They were tied at 28. Now Dalton is our top customer at 29. So we were able to quickly get a query that value because it's pre-aggregated for us by a bit more of denormalization. So you apply a little denormalization here, a little denormalization there. Oh, I'm frequently running that query to get that same that data. No, let's denormalize that. You don't have to denormalize everything, right? Like if it's books and authors, for each book, you might at least want the author's name, even if it's not their full bio, which is stored in the master data. So you denormalize the first and the last name so they're available for books without the extra queries that you would have to run to get them. So as we near the end here. Let's look at our final design. I've got one customer container. Inside that customer container, I've got documents of two types, customers and sales orders, which themselves have embedded three other types, an array of addresses, customer password, and an array of order details. All in one container. Partitioned on customer ID for the most common access patterns of that data. When I have different partitioning needs and different throughput needs, I want to store them in a separate container. So my products are stored in the product table. Actually, as I mentioned, we've got this down to 3 because product tag and product category, that's just small metadata, they're both partitioned on the same property type, even though the value is different between the two. They should really be stored in one container. So 9 tables is down to 3 containers. Now, at the risk of blowing your mind here, okay, what if I told you I could reduce this down to 1 container? You could. I wouldn't recommend it. I know people that do this. It really depends on your scenario. You could reduce this to 1 container. How? Because we're partitioning them differently. You can, and actually should, it's a best practice, to always name your partition key property PK, and then store a copy of the value from whether it's category ID or username or type, whatever it is, store a copy in PK, because that is immutable. You can never change the name of that property on a container without a whole migration story going along with it. So if I just made the partition key PK, and for customer and sales order documents, I store the customer ID value inside the PK property, but for the product documents, I stored a copy of the category ID in the PK property, and so on. That would still partition well, but it's going overboard because they do share different throughput needs. We need higher throughput on the customers than we do on products, and certainly on metadata that's often cached and much less frequently accessed. So we would provision very low throughput and pay probably the minimum 400 RUs, $24 a month on a product meta container, and raise the throughput levels on the customer and product containers accordingly to our needs, and pay more for the throughput on that data. So even though we could kind of hack the partitioning with that PK trick, it's going over. You have to know when to stop here. When you've achieved equilibrium and the force in nature is good all around you, then you leave it alone and say, that's good. Just let it be. So with that, key takeaways, ask questions while I pack up and rush off to my travels. You need to know your key access patterns. I am sometimes a bit oversimplifying this. Very often we see that customers do not realize what their access patterns are until they go to production, until this thing gets put out into the field, and then it's being used in ways they didn't anticipate. And now we have to re-engineer and remodel and figure out how to perhaps adjust our partitioning strategy. But if you have designed for them, then you will scale. Partitioning, obviously, is critical. If you want to achieve that scale and performance, you need to partition properly. How can you materialize relationships in a non-relational world? We saw embedding, we saw denormalizing, we saw pre-aggregating, and certainly storing related entities in the same container and even in the same logical partition to kind of get back the joins that you lose for your most common querying scenarios. How can you denormalize data? Sorry for that awful putrid green. You can use the change feed, you can use stored procedures. One thing about stored procedures, that transactional integrity that you get for the update, the commit or rollback, that is first of all, a very key critical feature. But beyond that, it is limited to the scope of a logical partition. Like you can only transactionalize updates, other documents that live in the same logical partition. It's not across the entire container, obviously. And with that, I want to thank you. I want you to feel free to contact me, reach out to me, visit my blog, follow me on Twitter. I want to thank you, and I really appreciate you attending, and have a great day. Thank you. Enjoy. Marek.